talk about sequences and series. And section 1 is really like a very broad view of sequence and series. Section 9.2 is going to be a specific type of sequence, arithmetic sequences, and then section 9.3 is going to be a very specific type of geometric sequence. So those sequences have something very special about them, but today we're just looking at all sequences, all series. Okay, so we need to talk about what those things are. Okay, to start with, we've got a sequence. That's like our warm-up where I had you list the perfect squares. That's a sequence of numbers that are related and have some kind of pattern. Those numbers are called terms. So we want to be able to use the correct language when we're talking about sequence and series. Each number in a sequence pattern is called a term. And sequences can be finite or infinite. When I gave you the warm-up, I said, list the perfect squares up to 10 squared. So everybody had the same list from 1 to 100. That's a finite sequence because we stopped. If I wanted my list of perfect squares to be infinite, I could write that list as 1, 4, 9, 16, 25, ... Okay, it just means and keep going. Don't ever stop. So we could keep going. 36, 49, 64, 81, 100, 121, 144, 169. Like we'll just keep going nonstop. Okay, so sequences can be finite or infinite. The mathematical definition for a sequence is really this next bullet point. So when I give you that first bullet point, an ordered list of numbers or terms, that's my definition in my own words. Just a list of numbers, basically. The mathematical definition, or the definition that you would read in your pre-calculus textbook, says a sequence is a function whose domain is the set of positive integers. A function whose domain is the set of positive integers. What would be the first positive integer then? 1, 2, 3, 4, 5, 6. So those are domain. Why we use those positive integers for our domain is they represent the numbered term in the sequence. So in the sequence that I have above with the perfect squares, my domain here is my first term, my second term, my third term. So my domain is 1, 2, 3, 4, 5. Okay, the domain is the numbered term that it is. Okay, the output or the range are the actual terms in the sequence. 1, 4, 9, 16, 25. Okay. Instead of function notation, so remember function notation is the one that looks like f of x. We're not going to use f of x when we work with sequences and series. We use something called subscript notation. And subscript notation obviously has a subscript. We usually use the letter A for sequences. Why we use A, I'm not particularly sure. You could use any letter that you wanted. And then we usually say A sub n. So A sub n would be the output, just like f of x is the output in a function. F of x is a fancy way to write y. A sub n is also a fancy way to write n. So in a sequence, if you're thinking about graphing a sequence, every point on the graph of a sequence would be the point n, comma, whatever a sub n is. So n is the numbered term in the sequence. If you're talking about a sub 5, we want which term? A sub 5. The fifth term. Okay. If I say a sub 120, then I want the 120th term in the sequence. Okay, so that number, that n, is just telling you the term that you are. So up here, I have my output values. I could label these output values, and it's really important that you're comfortable with the notation. 1 is a sub 1. 4 is A sub 2. 9 is A sub 3, A sub 4, A sub 5. So again, that whole idea that A sub 5 is really the 5th term. 25 is the 5th term in that sequence of perfect squares. And if I wanted to plot those perfect squares, I would, on a graph, plot the ordered pair 1, 1. I would do 2, 4, 3, 9, 4, 16. And what's really interesting about sequences on a graph, do not draw a continuous curve. Okay? They are only points. Okay, so in your graph, you would leave them as separate points, not as a line. This in math is called a discrete graph. So discrete means really not continuous. Okay? Those are those individual points. Okay? Do not connect the line. In a function, we would connect the line because we could do, really this is like x squared, we can do 1.5 squared. Okay? But in a sequence, do you have a 1.5 term? No, you have a first term, a second term, third term, that set of positive integers that's your domain. Okay, so you don't connect the graph. So that's a little bit about subscript notation. The last thing on this slide, the function values a sub 1, a sub 2, a sub 3 are the terms in the sequence. So again, the outputs of your sequence, whatever those numbers are, you can list them out. A sub 1, a sub 2, a sub 3. The subscript tells you what term it is in the sequence. So a sub 3 tells me that's the third term in the sequence. Okay. Now, I just said that the function's domain is the set of positive integers. Sometimes we'll start it at 0. And there might be special reasons we start it at 0. Okay. So don't be alarmed if you ever see an a sub 0. Okay. It just is that in some cases we would prefer that. If you're thinking about like a real world scenario, that might be representative of like a time 0 at the very beginning. You might actually want a y-intercept for some reason. So don't be alarmed. I'll say this, I generally default to starting at 1. Only when I'm told that there's an a sub 0 do I really worry about a sub 0. So there'll be some notification there. Does anybody have any questions about any of the stuff that we talked about on this slide? Really important to pay attention to the notation as we work through these 3 sections this week. Don't shy away from it today on day 1 because it's just going to get more and more heavily notated as we move through the chapter. Okay, so here's examples that we could do with sequences. And I think you're going to find, like, as long as you can read and understand the directions, like, this stuff is not going to be too terribly difficult. So my first example is write the first 5 terms of the sequence. Assume n begins with 1. Okay, so the book, I think, tells you today when n begins with 1 and when n begins with 0. Okay. So I've got a sub n equals 2n plus 1. Ideas for how to find our first term. Austin, say aloud. Plug in 1 for n, right? We want the first term, which we would identify as a sub 1. That would mean the first term to us. And if we write a sub 1, then we're saying n is really 1. So Austin is exactly right. A sub 1 is 3. We could do the same work for a sub 2. This time plug 2 in for n. We'll get 5. A sub 3, we'll get 7. And are you noticing a pattern? What's happening to each number? It's going up by 2. So I could probably at this point write out my first 5 numbers of my sequence, or terms in my sequence. 3, 5, 7, 9, 11. Now, when you're doing your homework problems, take the time to work them out if you need to. Some of those sequences you can evaluate in your head. Like I'd be able to do 2 times n plus 1 in my head, okay, and list the 5 terms. Some of them maybe won't look quite as nice, but the idea that Austin gave us rings true going forward. So write the first 5 terms of this sequence, and this sequence is maybe not as nice as 2n plus 1. But we're going to go with the same idea. To get the first term, plug in 1 everywhere I see n. So in the numerator, I have -1 to the first, which is just -1, times 3, that's -3, over 2 plus 1 is 3, so my first term would be -1. Do a sub 2. 3 times -1 squared, all over 2 times 2 plus 1. When I square -1, it will now be a positive 1 times 3, so I'll get positive 3, and then 4 plus 1 is 5. If I were going to do a sub 3, I'm going to squeeze this in, sorry about this, on the next one, what happens when you do -1 cubed? It's a negative, times 3 is -3, over 6 plus 1 is 7. Anybody want to, without maybe working it out, tell me what my next term is going to be? -3 over 3, which is technically -1. 3 over 5, -3 over 7, 3 over 9. If you kind of pay attention to the denominators here, 3, 5, 7, the next denominator is going to be 9. It's the same sequence we had before, 2n plus 1. And then your numerators, what's happening to that 3 in the numerator? -3, positive 3, -3, positive 3. So I could write out my sequence as -1, 3/5, -3/7, and then like Jesus told us, the next one's going to be 3 over 9, but that's really 1 over 3. And the next one should be a -3 over 11. Okay, so I got my 5 terms. Once you pick up on the pattern, you can go with the pattern. Okay, you might check one of the other ones later to verify that you're getting the correct solution, but it should work either way. Now, my question, this is my list for this problem over here, is what would change, if anything, if I just change one part of that sequence? 3 times -1 raised to the n plus 1, all over 2n plus 1. Does anything change for us? Jesus is saying no. Paige is saying yes. So let me go to Paige. If something changed, what would it be?
Well, I'm just like playing it in my head. So if you put 1 into like the numerator, I'll put it.
Do that. Play that out in your head, though. If you put 1 into the numerator, what happens to the numerator? It will be positive. So Wyatt, you would say what would change?
They just swap, like all the negatives would be all the positives.
The signs would swap, right? Everything that was previously raised to an odd was a negative term on the left sequence. And now on the right, if we have an odd term, we'll be adding 1, which makes it even, and then it will really be positive. Okay, so this is going to be 3 times -1 squared, which is going to be positive 1 times 3, so we're going to get 3 over 3, or positive 1. Okay, so the new sequence would be 1, -3/5, positive 3/7, -1/3, and positive 3/11. So does anything change? The signs change. And this is going to be helpful to you in your work today, in your examples that you do. If you see in a pattern, in a list of numbers, that the signs are changing, like alternating, positive, negative, okay? something that you can use to make it go positive, negative, positive, negative, positive, negative would be just multiply your rule, your term, your equation by -1 to the n plus 1. You can also do, and you might check in the back of the book, I mean, technically you could do n minus 1, right? Either way, you're getting back to an even number when you do the odds. Okay, so that would be, this would be used for positive, negative, so on. And then if you want it to go the other, negative, positive, if you want it to start negative, then just use -1 to the n. Okay. So that little piece of that formula is what's alternating the signs. Notice that if I didn't have those negative ones raised to the n or the n plus 1, everything would be positive. So the signs wouldn't change. Okay, so it's really that -1 to the n or -1 to the n plus 1 that changes things. Okay? Okay. Thank you. Write an expression for the nth term of the sequence. So now if I give you a sequence, 1, 5, 9, 13, can you write what I would call a rule for the sequence? So basically I'm asking you to go backwards from what we just did. If I give you the first 4 terms, can you tell me what a sub n is equal to? So I'm going to ask you on this one, talk about it in your small groups. What are you thinking? Are you seeing a connection between the numbers? Are you recognizing a pattern? How can you use that to your advantage to write the correct rule? Okay, go ahead and talk with each other real quick about that. Anybody have any ideas that might work? What's floating around out there? What are some ideas that you started with, though? Even if they don't work. Give me some idea.
N plus 1.
N plus 1?
That's N plus 4.
N plus 4. And why did you say N plus 4?
Goes up.
Oh, okay, very good. So I stressed like the idea of like first recognizing the pattern, right? So I think that's a pretty normal one for a lot of people to say right away, is that it should be N plus 4 because you're adding 4. This is actually, and we'll do it I think on the next slide, called a recursive formula, where in order for this formula to work, I have to use the previous problem, right? Like 1 plus 4 is 5. 5 plus 4 is 9. 9 plus 4 is 13. If I use the previous term, I'm totally golden on that. Except for that, like if I'm using these a sub 1 and a sub n, that would be 1 plus 4 is 5, and 2 plus 4 is 6, which would produce the sequence 5, 6, 7, 8, and that's not what we want, right? So how else can you represent adding 4?
We have like a different.
Yeah.
We 4n minus 3.
4n minus 3. So notice that Wyatt's formula still has 4 in it. And 4 times n is just really like a repeated addition. When you do 4 times 1, you're only adding 4 once, right? When you do 4 times 2, you're adding 4 twice. If you do 4 times 3, that's 12, you're adding 4 3 times. So use that repeated addition, okay? And if you just started with 4n, because you notice the 4 in the difference there, you will get 4 times 1 is 4. 4 times 2 is 8. But you really want to go back so that you are those first terms. If you do 5 minus 3, no, sorry, 4 minus 3, do my multiplication correctly, 4 minus 3, we get 1. If we do 8 minus 3, we get 5. If we were to do 4 times 3, we'd get 12, minus 3 is 9. 4 times 4 is 16, minus 3 is 13. So this one, think about this. When you go up by 4 every time, isn't that a lot like slope? Rise 4 over 1. Rise 4 over 1. So think about it when you see that constant adding 4, adding 4, adding 4. Think about it like a slope. Okay, now, not all sequences that you'll be asked to write will be linear. So not all of your rules will look like this. Here's one just to kind of get us thinking. One thing I would notice about this problem right away is the alternating signs, right? It goes positive, negative, positive, negative. And so I'm thinking about in my rule, I always do that sign issue first. I'm going to take -1, and then you could think about, like, do you want to raise it to the n? Because then if you did a to the first, it would be -1 to the first, which would be a negative number. And our first number is positive, so we could change our exponent. Instead of raising it to the n, we could write n plus 1. You can also write n minus 1. It can go either way. N plus 1, n minus 1 is going to get you that positive, negative, positive, negative, positive, negative sequence. Okay, so we got that part. And that's just going to take care of my sign issue. Can anybody find a pattern for those numbers? So now you can kind of ignore the signs. 2, 9, 28, 65, 126. What about these numbers? 1, 8, 27, 64, 125. What are those numbers? Perfect cubes. Are they related to 2, 9, 28, 65, 126? Close, right? So we'd be doing perfect cubes, n cubed, but we'd also be adding 1, right? It's really n cubed plus 1. So 1 cubed plus 1 is 2. 2 cubed plus 1 is 9. 3 cubed plus 1 is 28. 4 cubed plus 1 is 65. 5 cubed plus 1 is 126. So that's what I'm talking about. Like, not everything is going to be going up by 4 so that it's super easy for you to see the pattern. You need to think about other kinds of number patterns that you know about. Those perfect squares, perfect cubes, the powers of 2, 2, 4, 8, 16, 32. Even the powers of 3, 3, 9, 27, 81, 243, okay? You should be able to kind of think about those things and see if those are the numbers that you want. Now notice that I should put my rule in parentheses so that, like, whatever this is, it's getting multiplied by all of that, so that I don't do like a negative plus 1, because that would change things. If I did like a negative n cubed, and so I got like -8 and then added 1, I'd really get to -7. So I have to be careful with that. I should really do this part first. Cube plus 1. Okay. Get to, and then change the sign. Okay, so this is the thing I have to say about this. I can't do every sequence for you, right? I can only show you some examples and kind of try to prime your brain for this, but it's your job to look for the pattern. And you're going to be looking for the patterns outside of all of the normal patterns that we look for, like plus 4, plus 4, plus 4, plus 4. Some of them are going to be some other types of patterns. And you just need to play around with the numbers. Okay, sometimes it's something like this, where if you just add or subtract a number, it gets you to a list of perfect squares, or a list of perfect cubes, or a list of powers of 2, something like that. Okay, so kind of be cognizant of all those types of things. This is going to take us to, was it Austin that gave us n plus 4? Who was that gave us n plus 4? Yes. Okay, this is called a recursive sequence. A recursive sequence defines one or more of the first terms. So usually you just get one term, like they'll tell you what a sub 1 is. Sometimes you get multiple terms. And then all of the other terms are defined using a previous term. So this is like Austin, where in order for Austin's rule to work, I had to know what the previous term was. So I could do 1 plus 4 is 5. 5 plus 4 is 9. 9 plus 4 is 13. As long as I knew the previous term, I was able to get the next term. Okay. Here's an example of what a recursive sequence looks like. Okay. A sub 1 equals 6. Okay. Define the first term. So I now know the first term in the sequence is 6. Okay. All other terms are being identified in terms of the previous term. Okay, so A sub n is being defined in terms of A sub n minus 1, where n minus 1 is just the term before n. So, like, if I wanted to know A sub 5 in this formula, I would need to know A sub 4, and I would add 1. In order for me to know A sub 4, I would really need to know A sub 3. In order to know A sub 3, I would need to know A sub 2, and in order to know A sub 2, I have to know A sub 1. Now, if I backtrack all the way up to A sub 1, can I evaluate those now? Yeah, because I know A sub 1 is 6. So A sub 2 is 6 plus 1, which is 7. And A sub 3 is 7 plus 1, which is 8, 9, 10. Okay, so I could list out the first 5 terms, but then I'm just adding that 1 on to the previous term. Okay, so that's a recursive one. If we were then using, remember Austin's rule that he gave me for the previous problem, A sub n equals n plus 4, we would need to change his n, because it's not really the numbered term, right? It's the previous term, so we would change that to read A sub n minus 1. And then we would have to say that A sub 1 was 1. So we would know the first term was 1, and then we would just add 4 to the other terms. And that would generate that list, 1, 5, 9, 13. So that's called a recursive formula. The other formulas that you were writing on the previous slide, like the one that Wyatt gave us for n minus 3, those are called explicit. Explicit is nice because if I have Wyatt's formula for the one in blue, which was A sub n equals 4n minus 3, it would be really easy for me to say, hey Joe, what's the 20th term? And Joe would just do 4 times 20 minus 3, and he would tell me 77. Okay? If I ask Haley to give me the 20th term using that recursive formula that Austin gave us, Haley has to do 20 plus 4 is 24, or sorry, she has to do all, not 20. 1 plus 4 is 5, 5 plus 4 is 9, 9 plus 4 is 13, 13 plus 4 is 17, 17 plus 4 is 21. She's got to count up till she's at the 20th term. Okay, so there's a benefit sometimes to using one over the other. Okay, but that's called recursive. Okay, moving right along. I'm going to skip this one. Does anybody know what this sequence is? 1, 1, 2, 3, 5, 8. Does anybody know what the next number is? How'd you get 13?
Adding the previous number to
The 2 previous terms. 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, 5 plus 8 is 13. Yeah, that's called the Fibonacci sequence. So on this slide, all I was going to do is write out the Fibonacci sequence as a recursive formula. We'll skip that. Maybe we'll have some time later this week. We can go back and look at Fibonacci. Fibonacci is a really cool sequence that happens a lot in nature. Okay, so this is the other thing we want to get to talk about. It's called summation or sigma notation. Do not be scared off by the Greek letter sigma. Okay, and all the stuff that's happening there. It's just a quick, easy way for us to give directions. Remember, mathematicians, I would consider us kind of lazy, like we don't want to write as much words, so we find notation to do it for us. Okay, so summation notation is really this stuff over here. Okay, this is the Greek letter sigma. Okay. And all that summation notation is, it's a direction to add terms of a sequence. So notice on that right side, it just says a sub 1 plus a sub 2 plus a sub 3 plus a sub 4, so on and so on, all the way up to a sub n. Add all those terms in the sequence together. That's what that summation notation says. Okay. This is the Greek letter sigma, so I'm going to label this. That's why it's called sometimes summation or sigma notation. Okay. This is your index. Index doesn't have to be I. The most common letters for index are I, J, K, and N. So you can use any letter that you want. And the index first is given to you in terms of a lower limit. So notice it says I equals 1. The first term I start with is a sub 1. If this bottom piece right here said I equals 5, the first term in my sum would be a sub 5. And then I have an upper limit. Now, the difference is when we do actual problems, the upper limit is going to be given to us as an actual number. So instead of n, it will be like 5. And so we know we would add a sub 1 plus a sub 2 plus a sub 3 plus a sub 4 plus a sub 5. Okay. So that's your upper limit. And then this right here, this a sub I, okay, this is really just like your rule for your sequence, right? Okay, it's your equation for your sequence. So I'm going to write rule or equation for sequence. So that's how you're going to generate the terms, just like we did in that first example, like list the first 5 terms. That's how you're going to generate those terms that you're going to be adding together. You just plug the number into the rule. Okay. So summation notation is actually really easy once you get over the way that it looks. It just tells you what it wants you to do. Okay. So here's an example. Find the sum of the terms in the sequence 3i plus 2 for the second to the 5th terms. So what this is really asking me to do in my summation notation is do a sub 2 plus a sub 3 plus a sub 4 plus a sub 5. Okay, that's what this piece right here tells me to do. I can use the rule, the 3i plus 2, to actually evaluate what those things are. Okay. So for a sub 2, I would do 3 times 2 plus 2, that's 6 plus 2, so 8. Plus 3 times 3 plus 2, that's 9 plus 2, 11. Plus 3 times 4 plus 2, that's 14. Plus, maybe you're catching on, it's going to go up by 3, so it should be 17. And then now instead of having a sequence, just a list of ordered numbers, 8, 11, 14, 17, I have what is supposed to be a sum of those numbers. So then I could get out my calculator and add those up. Okay, so 8 plus 11 is 19, plus 14, that's 29, plus 4, 33, plus 17, that's 40, 50. Does everybody agree with me? Okay. So if you're doing a series, a summation notation or a sigma notation, that is going to be just a number answer. Okay, instead of a list of numbers, it's going to be one number that is the sum. Okay. I'm not going to take the time to do the whole example for this one, but I just wanted to show you because there are some factorial examples in the homework assignment. Does anybody know what 0 factorial is? So 0 factorial is 1, 1 factorial is also 1. And then you probably are comfortable with 2 factorial, we've been doing factorial, okay, is 2. So just so that you're aware of that, if you type that into your calculator, 0 factorial, it will give you an output of 1. Okay, I think about it like in terms of like the arrangements, because that's kind of like what factorials are. How many ways could you put out 0 items? One way, put out 0 items. And so 0 factorial and 1 factorial are both 1. Okay, so that will be helpful when you're evaluating those with factorials. Okay, last idea that we want to get to is the idea of a series. Okay. So when I was talking about summation and sigma notation, I used the word series and I kind of retracted it and changed it back to summation and sigma. But a series is a sum. It's a sum of terms of a finite or infinite sequence. Gonna be okay, Austin?
Yeah.
Okay, so this is really interesting and something for you to kind of be thinking about as we move forward in this particular part of the chapter. I'm saying that you could sometimes find a sum for an infinite number of terms. And that may be, if we're thinking about like one of those examples of the sequences, like that one we worked with that was going up by 4, 1 plus 5 plus 9 plus 13 plus 17 plus 21 plus 25, like that has no limit. It's just going to keep getting bigger and bigger. It's just going to grow to a positive infinity. But there are some sequences where your numbers start to approach a number, and so you could actually find a sum. We'll talk more about those infinite ones later, but just know that we are going to do that. We're going to find the sum of an infinite number of terms. Okay. The book will refer to an nth partial sum. Nth partial sum is for a finite sum or series. Okay, so it's saying, oh, and I have finite right here. The nth partial sum would say, like, if I say find the fifth partial sum, then it's the sum of the first 5 terms. Okay, so it's saying you have a sequence that might be infinite, it goes on forever, but I want you to find the sum of everything. I just want you to find the sum of the first 5 terms. Okay. You don't necessarily have to write these down, but just so that you're comfortable when you see them in the book, you should be able to immediately distinguish if you're finding the sum of a finite or an infinite series, right? If you have any number up here, it's going to be finite. So like a fifth partial sum, okay? If instead of a number you have infinity, then that's talking about an infinite sum. So just be aware of the notation. If there's an infinity there, then I'm referring to an infinite sum. Okay. Okay, so this is our last example. We see sigma notation here. We want to find the third partial sum and the sum. Okay, find the third partial sum and the sum. So in the book, I think they'll give you like part A and part B. So the third partial sum would change that so that it doesn't have an infinity as an upper limit. If I want a third partial sum, then 3 becomes my upper limit. And could you add this together? Sure, you would want the first 3 terms, right? A sub 1 plus a sub 2 plus a sub 3. That's a third partial sum. And then I would just plug those things in. 4 over 10 plus 4 over 10 squared plus 4 over 10 cubed. That's 0.4 plus 0.04 plus 0.004, 0.444. Okay, so that's my third partial sum. And just add the first 3. Could you imagine what would happen to the infinite sum if I just kept going? If I just kept going in the infinite sum, I'd be doing 4 over 10 to the first, plus 4 over 10 squared, plus 4 over 10 cubed, plus 4 over 10 to the fourth, plus 4 over 10 to the fifth, so on and so on, right? And what does each of these things do? Adds a 0. So it's just going to be 0.4 repeating. And so that would be my infinite sum, would be a non-terminating decimal on this example. So be careful when you get to those on the homework assignment. Make sure you read there are really 2 directions. I think they do list them as part A and part B. You do have a homework assignment. It should be on your gold sheet. We have selected odd problems so that as you work, you can check your answers in the back of the book. Please make sure you're doing that so that you know for certain if you're doing things correctly or not. You have a quiz over sequences on Friday. Make sure you're reviewing your notes, like the new notation and the definitions, so that you're feeling confident when you come to a quiz on Friday.